Okay, so today we want to introduce ECDLP, which is the elliptical version of the discrete logarithm problem. But of course, before we can do this, we have to properly define what are ellipticals when they are defined over a finite field. And so let's start from the beginning. Remember, we'll consider a finite field of the form Fp. And then we gave the definition of elliptic curve as satisfying a Weierstrass equation of the type y squared equal x cubed plus ax plus b. And then the condition was that the discriminant, the determinant, is 4a cubed plus 27b squared, and this is not 0. Okay. So what is then an elliptic curve defined over a finite field is exactly the set of points, like we would imagine over the real numbers, is the set of points that satisfy the equation, right? So the elliptic curve defined over Fp is the set of points x, y, such that essentially this equation is satisfied with the x and y when x and y are elements of the finite field. Okay. Of course, to this we have to add the point at infinity to make sure that the curve is well defined, and then the addition operation of points is well defined. So let's go through an example. Let's consider the following curve given by y squared equal x cubed plus 3x plus 8. And let's consider the field F13. So we'll consider the set of points of the curve over F13. Okay, so how do we even find such points? We have to see which points verify the Weierstrass equation. So one way to do it is similar to what you do with curves in college algebra. Essentially, you start from the x and then see what the corresponding y is. Of course, in this case, we have to verify if y actually exists. And here is an example. If I start from x equals 0, which is always the first point, with the first value in every finite field, then we get that y squared is equal to 8. Because of course 0, 0. So if y squared is equal to 8, then there is no actual such y, because 8 is not a quadratic residue, is not a square modulo 13 if you want. So there is no point starting with 0. On the other hand, if x is equal to 1, then this leads to y squared being equal to 12. And then when we look for roots of this, then actually we have two values, y equal 5 and y equal 8. So then this leads us to 2 points. Well, first of all, so this set of points with the elliptic curve consists originally of the point of infinity first, for sure, and then we just added 1, 5 and 1, 8. And we keep doing this procedure for 2, for 3, for 4, and all the numbers modulo 13 up until we get to like 12. 12 is also of this kind, so we get 12, 2 and 12, 11, and in total we get 9 points. Okay, you have this on the book. We are now looking at section 5.2. Okay, so we get 9 points on this curve. They form the set of points. So now, how do we define the addition of points in this environment? So of course, one thing that we could do is to just look at the theory of the geometric approach using the field Fp instead of R, and it's a little bit more complex. This leads to an area of mathematics which is called algebraic geometry, and it's very fascinating, but it's kind of beyond us at the moment. But instead, we can refer to the formulas that we gave last time to just simply add the points. And so we take 2 points P, right, and Q, and we define the addition of points P plus Q to be the point like x3, y3 with the formulas that we gave last time. And then what we can verify, because of course the thing that is not obvious is that when you get two real numbers, you add them and you do the formulas and you end up among the set of points. But here it's even less obvious because we're talking about finite field objects, and it is not even clear that this new point x3, y3 actually is going to end up on the curve again, especially because we see that the number of points on the curve is now finite. Okay, so then in fact we can use this result, which tells us that two things. If you take E to be an elliptic curve defined over Fp, and we take 2 points P and Q in this set, then the addition also belong to this set of points. And then, in fact, the addition law, so the plus, satisfies all the properties that we defined before, and in particular in theorem 5.5. So these are the properties of a group. Okay, so this makes E of Fp with plus an additive group. Okay, because it's closed under addition and it satisfies the existence of an inverse and so on. Okay, this is great. So we're not going to prove this, but we can certainly make use of it. And let's look at an example using the same curve that we were using before and see that this is actually making sense. Let's take 2 points P, this is the point 9,7, and Q to be the point 1,8, right? They both belong to the curve defined over F13 that's given by this Weierstrass equation. And then let's compute its addition. Of course, the first thing that we need to do to compute P plus Q is to compute the lambda. And this, remember, is given as a slope, so it's just y2 minus y1 over x2 minus x1. In this case, this yields 8. Right? Of course, you can do your calculations. Remember that every time you get, for example, a denominator here, this would be 1 over 5, and we have to really think about this as like the inverse of 5, right? Modulo 13, which is, of course, 8. Okay? So remember that all these computations are performed in the finite field. Now that we've got the lambda, then we can compute the points, right? So we will start with x3. So the coordinates, that's what I meant. And so x3 is going to be lambda squared minus x1 minus x2. We got all the info here. This is going to be 64 minus 9 minus 1, which gives us 54, which is 2. And similarly, we can compute y3 now, and this gives us 10. And then, so we get the point P plus Q, which is 2, 10. Okay? And in fact, it's possible to verify that the way that this is one of the points among this set, that we didn't write it explicitly, but it certainly verifies the Weierstrass equation. And so this shows that the addition of 2 points, I mean, at least gives us an example of how the addition of 2 points ends up being in the group again. Okay, we can do a similar calculation to add P to itself. Remember that in this case, your lambda will be something different because it will be the tangent, right? Again, the process will yield a point in the group. In this particular case, if we sum P plus P, we get the point 2P, which is 9,6. Okay. Excellent. So, in fact, because this is a group, I can write down, as you normally do for groups, the table with the operation. And so when the group is multiplicative, this is a multiplicative table. or otherwise it's an additive table, but the substance is the same. And here you have the table. I'm going to zoom in a little bit so you can see how each point sums with each other. Of course, we know that the point at infinity serves as the zero in the group. So whenever you sum it with a point, you get the point itself and whatnot. Okay, so here you have the complete group law all written out. Okay, so now that we have nailed down what an elliptic curve is over a finite field and how to add points, well, let's try to have a closer look at this set of points, because we did say that essentially E of Fp is finite. So there's finitely many points, and so exactly how many points do we expect to have in there? So here's the thing. Essentially, for each x, there are two possible y's, right, at most. And in fact, we expect at most to have 2p plus 1 points, because there are exactly p different x's in the field of p. Okay, so this is like a hard upper bound for the number of points of the curve. Let's say it's an upper bound. Yes. Now, of course, this is not true in general that every value of x gives me 2 y's. We already saw an example up here. So what we can do is that we can analyze it a little bit more precisely. And so, in fact, when we plug in a value for x, and again, in principle, we have at most 2 possibilities for y, there are, in fact, 3 things that can happen if the value of x is a residue mod p, then I get 2 solutions. Otherwise, x is a non-residue mod p, in which case we get no solutions, and that was the case with x equals 0 up here. Or otherwise, it may equal 0, in which case we do get 1 point. So otherwise, the solution leads me to y equals 0, which does give me a point, but this is very rare. So what happens is that this happens with about 50% of the times, and this about 50% of the times. Okay? So yeah, in other words, I'm saying that finding a root of the Weierstrass equation is extremely rare when we put things into perspective. And so we really expect the number of points in the curve to be approximately 50% of this, which means is approximately like p plus 1. Okay, the plus 1 is again because we're adding the point of infinity. So this is like quite close to the actual scenario. And to conclude this first investigation, we cite a result by Hasse, which tells exactly that if I consider an elliptic curve over Fp, then the number of points on this elliptic curve is given by p plus 1 minus this quantity Tp, and then Tp is satisfying this inequality, so it's bounded by at most to the square root of p. Okay, so this quantity here, this quantity Tp, which we define in the other way around to be p plus 1 minus number of points of E over Fp, you can now see that this is, in a sense, an identifier of a specific curve. So for each curve, we get a different value Tp, which is called the trace of Frobenius. Okay, of E over Fp. Okay, so this serves as an identifier, and it's kind of like almost like a linear transformation over a two-dimensional space. So this becomes then a little bit technical, but the idea is that it gives an indication, right? So it's bounded by at most 2 square root of p, and so we expect this to be the number of points in average of a curve. Depending on the value of p, of course, this trace changes. And so here, for example, suppose that we take a specific curve that we want to look at, right? Let's take the curve y squared equal x cubed plus 4x plus 6. And then let's see where this value lies, right? And what is TP, and how close it is to the 2 square root of p. And so we can do this experiment for p equal 3, 5, 7, all the primes, right? And then the result, it would be easier to see here. I can even zoom in a little. Right? You can see that when p is equal to 3, we get exactly 4 points on the curve. TP is 0. This is obviously quite far from the value of 2 square root of p. When p is 5 is 8. So TP is negative 2. And in order of magnitude, our TP is always kind of close to this value here. Sometimes a little bit less, sometimes a little bit more, right? And the number of points here is always kind of close to p plus 1, right? That was our idea. In this case, it's exactly p plus 1, 3 plus 1 is 4. Here, p plus 1 is 6. Here, p plus 1 is 8. So we're always close to p plus 1, right? Here you can say, for example, 17 is p plus 1 is 18. So the number of points is a little bit less. So in some cases it will be a little bit less, in some cases it will be a little bit more, but it's anyway bounded by this quantity. And so when we look at it in perspective, this gives us a good indication of how many points we can expect to be on the curve. Okay, so now we've defined curves over the field, and we defined we looked at how many points are on the curve and how many points we can expect on the curve in principle. And so the next thing is now, because I promised we would look at the elliptic curve discrete logarithm problem. So let's start by recalling the actual discrete logarithm problem, right? So what was DLP? DLP in general, and this is the beauty of formulating it as a generic problem. If we take a group G and two elements G and H, right, such that H is G to the X for some X, find X. Okay, and so what is peculiar is that we're using always multiplicative notation for this group in general. I mean, there is no, you can use a generic notation if you want, but how you associate the elements is always either as a power or as a sum. So here we're thinking of G to the X as G times G times G X times, because we're using the multiplicative notation. But we've just seen that, in fact, the elliptic curve over a finite field forms a additive group. And so when we think about ECDLP, we have to translate this additively, right? And so the idea is going to be the same. We fix an elliptic curve over a finite field with the addition operation that we know and love. And then we take 2 points, P and Q, in the set of points, and such that Q is now what exactly? Well, here we had G composed with itself. The composition operation, the operation of the group was the multiplication, but now our group is additive, so it would be P added to itself several times, right? So it would be a multiple of P, because we're thinking that NP is like P plus P plus P n times. Okay, and this is the formulation of the elliptic curve discrete logarithm problem given 2 points on an elliptic curve such that one is a multiple of the other. Find n. Okay, in this case, n is exactly defined to be the discrete logarithm, right, in base P of the point Q. Cool. And so, of course, now this is interesting. Our definition is not super precise in principle. You know, it may be that Q is not a multiple of P, or there doesn't exist this value. But of course, if we're using this for cryptography, then this will be generated as an honest instance. So we start from the P and generate the Q as a multiple, so then it's always well defined, right? Now, the second thing to consider, so the first thing to consider is that in cryptographical instances, this N is exactly my secret. So P is a public point, and then I choose like a random multiple of it, and then I will publish Q, right? So it is well defined. Not in general, but for our purposes it is. And then the second thing to consider is that, of course, for every P, there exists always a value S, such that SP is equal to the point of infinity, right? And this is also intuitive because the number of points on the curve is finite. So at some point there must exist, so the proof is not hard, at some point there must exist one multiple if I keep adding with itself so that I go back to the point of infinity. Okay, so in fact this integer here is called the order of P, right? And so we also know that the order of P divides the number of points, right, and so on. All the properties that we know about groups. I mean, this is a group, so it works in just the exact same way. So what this is telling us, in fact, is that once the logarithm is defined, then it is also defined modulo S. So we can really think that this logarithm is an element of ZS. Okay. Again, we take in modulo the order of the element that we are dealing with, like we were doing for the original discrete logarithm problem. And what is important about this is that in fact this gives us access to the fundamental property of logarithms, which is that the logarithm of, well, now remember that my group is additive, so if I do Q1 plus Q2 in base P, then this is equal to the log Q1 plus log Q2. Okay? And now if you're like, okay, this is not exactly how I remember the property of the logarithm, but you have to think a little bit more broadly. So if my group is multiplicative, I have that log alpha times beta is the same as log alpha plus log beta, right? And we all know this property here, but we know it in this form. We always think like, oh, the logarithm of a product is the sum of the logarithms. We kind of like downgrading operations, because when we deal with real numbers, this is what happens, that our group here is multiplicative, right? And then we end up somewhere additive. But here we're already starting from an additive group, and yet the law yields just the same. And so the real reason for this is that in fact we are mapping, right? We are mapping, in this particular case, we are mapping the set of points of the curve over the finite field to ZS, right? And this is because, in fact, the discrete logarithm is a group homomorphism. So if you remember what a homomorphism is an operation that preserves, it's a function that preserves the operation, and of course we're going from an additive group here to another additive group here, so that's why we see the logarithm law in this kind of unusual form. But here, if we are applying the same discrete logarithm to a multiplicative group, and then we end up again in the additive group, which is modulo the order of the element that we're taking, right? Remember, this is like log base G or whatever. And then that's why we map now a multiplicative group to an additive group, and then we have this kind of like our multiplication turns into a sum, stuff that we know about discrete logarithms. Okay, so this is interesting, and it's a very important concept. Let's just for fun look at an example of discrete logarithm problem with the same curve that we had before, the y squared equal x cubed plus 8x plus 7. You know, we don't like to do numerical examples, but it is certainly sometimes useful to just put things into place. Let's consider a non-trivial field like F73. 73 is certainly a prime, and let's consider the 2 points P, 32, 53, and Q to be 39, 17. Okay, and then what we can compute with the usual sum operation is you sum P to itself several times, and in the end you'll find that Q is 11 times P. Okay, and therefore we set the logarithm base P of Q to be 11. Okay, now if we choose another okay, so now what we can say is that if we take the number of points, how many points do I expect to be in the curve? About P plus 1, right? So one thing that I can check is that the number of points over Fp is, in fact, I can count them all, it's 82 of them. And what happens is, what I was saying before, that not necessarily my point has maximal order. So in fact, in this case, we have the P as order 41, because 41 times P gives me the point of infinity. And so the order of P is 41, which is 82 divided by 2, right? So we did say that the order has to divide always the number of points, the order of the group. Okay, so in fact, half of the points in the group are multiples of P, and the other half are not. So in general, this discrete logarithm problem with P as a basis is not well defined. Of course, again, if we're doing this for cryptography, we start from P and choose a random multiple, so this is always well defined. Okay, so hopefully this makes sense. And so now we've got the ECDLP defined. We really want to use it to do cryptography, but there's like one last thing that we need to check, and we'll do it quickly. I mean, there's an entire, so in section 5.3.1, you have more details than you need. But essentially, we want to make sure that we can actually use this efficiently, right? Because, I mean, we kind of expect this to be hard. First of all, because it looks hard to recover n from P. Like, these points don't look like alike at all. I mean, of course, I do need my group to be big, because otherwise I can just like search through and try all possibilities, right? But barring that, it does look hard in general, and we also know that the discrete logarithm problem is hard in general. So we certainly expect this to be hard, but we also want it to be easy to compute for the honest user. And so for this, we actually need an efficient way to add points. So in generic groups, we had presented the square and multiply algorithm, which consisted of taking the binary decomposition, right, and only taking the relevant powers. So we just do squarings and then multiply with the next one, right, because it's squared, because we're doing binary decomposition. So we can do a similar thing, and of course, what happens is that we're now in the additive realm, and so by analogy, a squaring is really just a doubling. So my algorithm become a double and add algorithm. Okay, and so the underlying idea is the same, is that we decompose our number n in binary form as like n0 plus n1, 2, or 2 and 1, right? Plus n2 times 4, and all the powers, up until like nr times 2 to the r. And then every time, this is a binary decomposition, every time an ni is a 1, then I'm doubling my point. And every time it's a 0, I just ignore that. And then I sum all these doubles, all these multiples of p. Okay, so here is an example. Let's consider the curve given by y squared equal x cubed plus 14x plus 9. Let's take the point P to be 6,730. Let's take FP to be F3623, so things start to be like not trivial anymore, and consider the multiple of 947. So 947 times the point P. So if I have to do 947 additions, this becomes quite tedious. But in fact, what I can do is that I can write n as, this is 947, so it's 1 plus 2 plus, then the next multiples are not there all the way up until 2 to the 4, then I have 2 to the 5, then I have 2 to the 7, then I have 2 to the 8, and then I have 2 to the 9. Okay? So by a simple calculation, this requires 9 doublings and then 6 additions. Now, a doubling is the same as an addition, of course, in exactly the same idea for which a square is the same as a multiplier, just multiplying with itself. So in total, you have 15 operations, right? And this is still much better than doing 947 additions, of course, right? Much better. And in fact, what we can check is that this is kind of like logarithmic in size, right? So if I have that my number k, if I call k to be approximately the logarithm of n, then with the double and add, if n is of the form like the worst case scenario is that this is like 2 to the k minus 1, and then I have like at most, and I have like all the powers there, then I have at most 2k, so like 2 log n roughly, right? So that's why I say it's logarithmic in size. I have like 2 log n, what we call point operations. So in this particular case, like point additions. Okay. In fact, what is interesting is that I can do even better in this case if I allow not just for sums but also for subtractions. And again, an example in this case is extremely helpful because what you can see is that you can easily sum. So this was not necessarily the case for generic square multiply algorithm because computing the inverse is non-trivial. But in the case of a subtraction, the point is that if I have minus xy, this is the same as x negative y, and therefore, you know, where we were trying to do the square multiply algorithm, if I have to compute an inverse, this is expensive, right? I have to use the extended Euclidean algorithm or something else. Here, using a negative is actually basically free, so we can actually use subtractions and see if this leads to less operations. In this particular case, 947, in fact, I can write as 1 plus 2 minus 2 to the 4 minus 2 to the 6 plus 2 to the 10. So you see that this, instead of taking 15 operations, takes less. I mean, in this particular example, what we can do is that we can do 10 doublings plus 4 additions, and this leads us to 14 operations. 10 because this is like the 2 to the 10, right? And so already here we have a little advantage. Of course, this is just a toy example, right? But we can see that this technique is interesting. So what we're really doing is that instead of doing binary, we're looking for ternary expansions, which means that my coefficients can be 1, 0, and negative 1. This is why it's ternary, right? Basically, this is F3. Right? And if I write a ternary expansion, so of course this is an example, and you could tell me maybe you just got lucky and you only ever gained like one operation anyway, so what's the point? But in fact, what you can see is that in the worst case scenario, what we got is that we have 2 log n operations in the worst case for double and add, but if you allow ternary expansion, then we never get essentially more than like k doublings plus a half of k adds, which is in fact 3 over 2k. And if you compare this with the 2k that you had here, remember k is the log n, then obviously this number is strictly less than 2k. Okay, so this is valid in the worst case, and even in the average case, we can compare the numbers and see that usually, essentially, if you take the boundary expansion of a random number, you have about 50% chance of getting a 1 and 50% chance of getting a 0, so you have about half of it. And so using the binary expansion of n, so this is like the worst case. But if you look in an average case, the binary takes on average k doublings plus 1/2 k addition. So it's 3/2 of k, right? That's because it's k doublings because it's half of them. But if you use the sums and difference, then what happens is that in fact about 2/3 of the terms are 0. And so in fact you can show that this will take you at most 4/3 k plus 1. And again, this is the smaller number. So, then we get an advantage here. Cool. So we have now the elliptic curve over finite field. We have the elliptic curve discrete logarithm problem. We know how to sum points efficiently, and I think so we are ready to actually explore finally how we use the elliptic curve discrete logarithm problem. So this is maybe the easiest part, because at this point, what we do is just we take the previous protocols, right, and we try to translate everything. So let's see how elliptic Diffie-Hellman works. The setup involves, of course, setting up a point P, a large prime P, and then we choose an elliptic curve defined over Fp, right? And then we choose a point in E of Fp. And this is going to be all my setup. Exactly like I did for discrete logarithm, where I had like a group and then I take a point and so on. And now I have here Alice and Bob that are trying to communicate, and they will do it in the expected way. So Alice will take P and will compute her own multiple of P, call this like QA, and Bob will do the same thing. So QP is like NB times P, and then they exchange these values. And then, of course, Alice will take the value from Bob and apply her own multiple to that. Bob will apply his own multiple to QA. And in the end, they both will have computed the point NA and BP. Bob, of course, has NB and AP, but this number and this number are the same. So if you sum a number with itself 3 times and then 5 times, and then you do 5 times and then 3 times, it's the same thing. In the end, you get 8 times P, right? So, so it's easy to show that they agree on this shared value. And then, like it looks like everything kind of translates in the same way. So, for example, we have the elliptic curve Diffie-Hellman problem, which is exactly the one where given n1p and n2p, compute the n1 and 2p point, right, which is the equivalent of like given g to the a and g to the b, compute g to the ab. We also have a decisional version of this, and so it definitely looks like we can translate most things in the same way, but we will see in fact that this is not exactly the case, and this is an important difference.